In this lesson, we're talking about, again, the exponential and our logarithm functions and the inverses of each other, but we're going to be focusing on now the graphs and tables and equations. So looking at the example one and you try one, before we get into it, just keeping in mind that when you are identifying the inverse, we're basically swapping the x and the y values. So like if you recall, remember that f of x is the same as y. So here, what we're doing is to get the inverse of a table, all you're doing is just switching the x and the y values to get the inverse. Now here, this notation that you see, this notation with this -1 exponent, what it looks like here, this is our notation for the inverse of f of x. When you see this f of -1 here, f to the -1, this represents the inverse. So if I just wanted to know what is the inverse of this table here, which is represented by our function 2 to the x. So like, for example, if I had 2 to the -2, that would get me 0.25. 2 to the -1, that's 0.5. 2 to the 0 is 1, 2 to the 1 is 2, and 2 squared is 4, and so on. So like if I had 3, then 2 to the third would give you 8. And then of course you could graph that in Desmos and see the table as well. So if I wanted the inverse, then the inverse would be, well, 0.25, which was my y, is now my x, and now -2 is my output or my y value. So notice how to get the inverse, you are switching the x and y values. So like here in this you try, first off, notice how you have the inverse of this function here. Because remember, exponential and log, they are inverse functions. Notice how you have that base 2 here. So we already have also the inverse equation, which means I'm going to take my inverse table, which is now going to actually be my log. So here, and if you were to graph this in Desmos and create your table, you'll see that this is the table that represents the log. So what is going to be the inverse table of values here? Well, it's going to represent the 2 to the x, because that is your inverse. So again, back to -2, 0.25, -1, 0.5, and so on. So notice how you are right back to these inverse functions, switching the x and y value. So then if we were to take these tables and graph them, here you have the graph of 2 to the x and log base 2 of x, which are inverse functions. And if I were to sketch the line y is equal to x, which is here and going through that diagonal, because if you're saying y is equal to x, then you're saying if x is 1, then so is y. 1 is equal to 1. 2 is equal to 2. -1 is equal to -1. So this is what you're plotting, which is basically, here, let me change the color. So you have this y is equal to x. And if I were to graph this y is equal to x line on the graph, notice how not only can you, of course, see the inverses, how we flip the x and y values, but also notice how they are a complete reflection of each other over that y is equal to x. So notice how anytime you have an inverse of a graph, you are reflecting over y is equal to x. So now here, let's go through and we'll do a quick sketch, and then I'll show you in Desmos so that we can check our work and see. So remember here, if we're sketching the inverse of 1/2 to the x power. So our base is 1/2. Notice how we have a decay. Well, here I notice, let me identify my points that are given to me. So on my graph here, I've got -2, 4. Here is -1, 2. Here is 0, 1, 1, 0.5. And then we could approximate this, but I'll leave this for now. Which means if we wanted the inverse values, then they would be switched. So instead of -2, 4, I'm going to plot 4, -2, 2, -1, 1, 0, and 0.51. So notice how, again, you're just flipping the coordinates and 0.51. So notice here how we're starting to get that curve here. And keep in mind too, another way of seeing inverse functions, that if this graph has the asymptote at y is equal to 0, then that means the other asymptote needs to be x is equal to 0 for the inverse. So now just to show the graphing, now keep in mind, if I wanted to know the inverse, then this would be not an exponential, but now a log, and then log base 1/2 of x. So if I were to graph these here, notice how here's our 1/2, and then here you go. Notice how, see, we've got that curve here. This is what we just sketched and graphed. Now, if we wanted to check the table of values, so notice how here now we stopped at the 2, but we could approximate it, so that was 0.25. So notice how here our values match our points here. And then now notice how we have the different values, but we could change these values if we wanted to. So notice how -2 is undefined, -1 is undefined, 0 is undefined. Well, we're back at it though with 1 and 2. So what if we put in 4? That means if I put in 4, then we should get the output of -2 here. So let's see. So if we put 4, sorry, let me get this down here. So if we put 4, there you go. Notice now how we ended up with that -2 value. So same thing, let's do another. So if I put 0.5, then we should get 1. Or how about this? If we put 0.25, we should get 2. So I'm going to put now 0.25, and right, we should get 2. So 0.25, and there's your value of 2. So notice how, again, all of these values are just getting switched here. So go ahead and pause the video and try and do a quick sketch of the inverse of this graph, which is the log base 1/4 of x on your own. And here we go. So again, I'm going to identify points here. So I see here I'm at 8. And then not necessarily at -2 or -1, so -1.5. Here I'm at 4, -1. Here we're at 2, -0.5. And here my x-intercept, which is at 1, 0. And then here we've got 0.5, 0.5. And we could estimate, but then notice how we're getting to that asymptote here. So that means if we have an asymptote at x is equal to 0, then that means the asymptote for your graph should be y is equal to 0. So then here, first off, if we have a base of 1/4, then that means we're going to end up with 1/4 to the x. So that is your base here. And then again, we're going to switch those coordinates. So instead of 8, -1.5, now I've got -1.58. Then -1, 4, -0.52, and 0, 1, as well as we could have 0.5, 0.5, which just really stays the same. So we've got 0.5, 0.5, 0, 1. Oh, sorry, I just realized that was my 0.5, my fault there. So that was 0.5, 0.5, 0, 1, negative 0.52, negative 1, 4, and negative 1.5, 8. So here is what the graph ends up looking like. And notice how you get that asymptote, and they are a reflection over y is equal to x. And so now getting into the equations or functions here, we're going to write the inverse. And same thing. Think about the table, right? Inverses, we switch the x and y. So f of x, remember, is the same as y. So y is equal to 3 to the x plus 1. The first thing we're going to do is to write the inverse. We are literally going to switch the x and y. So now x is equal to 3 to the y plus 1. And now we're going to solve for y. Now, think about when we solved our radical equations, right? If I had the radical, we always had to get the radical by itself. Well, notice how, yes, this is all in the exponent, but this is 3 to an exponent. So this exponential is by itself. There's nothing outside of it being added or subtracted or multiplied or divided. So now I can continue with writing the inverse, which is writing the log. So here we've got our log. Well, what is the base of our log? Well, the base is 3. So log base 3 of x is equal to y plus 1. Because remember, the equation is always equal to the exponent. So now that I've got my equation, the log base 3 of x is equal to y plus 1 set up, now we can continue solving for y. Well, what do we need to do? Well, if we're adding 1 to y, I need to subtract 1 from y. So now we've got log base 3 of x minus 1 is equal to y. And this is the inverse of our original function. So go ahead and pause the video and try this try on your own. And here we go. So again, we're going to switch the x and y. So x is equal to 2 to the y minus 3. And again, notice how our exponential, nothing is outside of it. So we can continue and write this as a log. So log base 2 of x is equal to y minus 3. Because again, remember, the equation is always equal to your exponent. So now notice we're solving for y, but we're subtracting 3. So now you should add 3 to both sides. So you've got log base 2 of x plus 3 is equal to y. And this is the inverse function of the original function that was provided. And so same thing again, but notice how we're writing the inverse of a logarithm. So here we're going to end up with an exponential. Keep that in mind, right? Because if I'm writing the inverse of a log, then I need an exponential. So same thing again, we're going to switch the x and y. So x is equal to log of y plus 1. Now again, notice how this log is technically by itself. See how all of this, the y plus 1, is all grouped together? So I can now go ahead and write this as my exponential. Well, keep in mind, remember here, if there's no base here, this is a common log, so it's understood to have a base of 10. So to write the exponential, I've got base 10 to the x power, right? Because remember, your equation's always equal to the exponent, which is equal to y plus 1. Now we can solve for y. Well, if we're adding 1 to it, subtract 1 from both sides. And you've got 10 to the x minus 1 is equal to y. This is the inverse function of this logarithm here. Go ahead and pause the video and write the inverse of this logarithm on your own. And here we go. So again, I'm going to switch the x and y values. So x is equal to log base 4 of y minus 2. Then again, notice how this logarithm is by itself. There's nothing outside of it. See how here the y minus 2 all grouped together by parentheses. So now we can write it as the exponential. So our base of 4, so base of 4 to the x power. Because again, right, remember your equation's always equal to the exponent, which is equal to what? Y minus 2. So now to solve for y, add 2 now to both sides. And here you've got 4 to the x plus 2 is now equal to y. This is the inverse of the original function. And so now in example 5, we're going to write the inverse of this exponential. Well, notice though, so actually no, here, let's do this. We'll go ahead and switch the x and y. So maybe you would have noticed what I was about to say. So x is equal to 2 to the y plus 3. Now notice the difference in what we've been doing and now this exponential that we need to write the inverse of. Is the exponential by itself? No. See how we're adding 3 now? This plus 3 is outside of the exponential. So just like our radical, we've got to get this by itself before we start writing this as a log. So I'm going to subtract 3 now from both sides. So 2 to the y is now equal to x minus 3. See how now the exponential is by itself. Now we can write this as our log. So again, log base 2, because the base is 2, of x minus 3 is equal to y. Because again, here, remember, your equation's always equal to the exponent. And notice how that's it. We were solving for y, and y is equal to this. So this means here, now first off, I just realized something. I'm actually not done, because this is actually different than this. And we do now need to include the parentheses here, because notice how we do have that expression x minus 3 altogether. So it actually needs to stay all together, not separated like what we had before. And there is a difference. So this is the inverse of our original function. So go ahead and pause the video and try this. You try on your own. And here we go. So again, switching the x and y. So x is equal to log of y minus 5. Now notice we're starting with a logarithm, and is it by itself? No, because see how now this minus 5 is outside of the parentheses, it's outside of our log. So we got to get the log by itself and add 5 to both sides. X plus 5 is equal to log of y. Now, again, notice here, right, if you needed a reminder, see how we have this expression here. So keep that all together when you're writing this exponential. Remember, though, you had this common log, so it's not a base y or a base 2, right? This is base 10. So you've got 10 to the x plus 5. Because remember, your equation is always equal to the exponent. So this is the full exponent, x plus 5, which is equal to y. And notice how y is already by itself, and this is the inverse function. So now example 6. Notice again, we're starting with a log, so we are going to end with an exponential. So let's switch the x and y values. So 7 times log of x plus 2. Now notice the log is clearly not by itself, but now there's 2 things happening. We are not only adding 2 to this log, but we are also multiplying it by 7. See how it's connected? So treat it like a 2-step. We always add or subtract first. So I'm going to subtract 2 from both sides. So x minus 2 is equal to 7 times, if we need to, we can add that dot there, represent multiplication, log x. Now, again, we still got the log got to get the log by itself, but it's being multiplied by 7. So now I'm going to divide both sides of the equation by 7. So now x minus 2 divided by 7 is equal to log of x. So now notice This needs to stay all together. X minus 2 divided by 7. Now we can write this as an exponential. Well, again, notice how you have a common log. So what is the understood base to be? 10. So base 10, so 10 to the x minus 2 divided by 7. That is all the exponent is equal to, I'm sorry, I put x here when I was supposed to put a y. I noticed that now, my fault, is equal to y. And this is the inverse function. So go ahead and pause the video and try this U-try on your own. And here we go. So notice how we've got this inverse. We're finding the inverse of an exponential. So remember now in the end, we're going to end up with a logarithm. So here, let's switch it. So x is equal to 4 times 3 to the y power minus 1. So to get the exponential by itself, right, before we can write this as a log, remember here, we're multiplying it by 4, the exponential 3 to the y, and we're subtracting 1. So treat it like a two-step. Always add or subtract first. So you should have added 1 here to both sides. X plus 1 is equal to 4 times 3 to the y. Now you're still multiplying the exponential by 4, so now you need to divide both sides of the equation by 4. Get that exponential 3 to the y by itself. So now I've got x plus 1 divided by 4 all together. Now we can write this as our log. So log, what's the base? Well, the base is 3. Log base 3 of x plus 1 divided by 4 is equal to the exponent, which is just y. Notice how y is already by itself, and so you're done. This is the inverse of the original function. So again, just keep in mind that the inverse of the logarithm is an exponential and the inverse of an exponential is a log. So if you're given a log and you're asked to write the inverse, you need the exponential. Same thing here, if you're given an exponential, you're going to end up with the log.